Okay, so I'd like to now look at an example to, I mean, we've talked in very abstract terms up to now. So let's try to make it a little bit more concrete. And being a mechanical engineer, I'd like to focus on a spring mass damper system. So let's consider this case. This is like ground or fixed wall. It's a one-dimensional system. So you can think of these masses M1 and 2 as being constrained to be able to move only in a horizontal line. Maybe they're like on linear bearings or something like that with zero friction. So I've got a mass M1 and a mass M2. M1 is connected to ground through a linear spring with spring constant K1, and then there's a second linear spring K2 connecting mass 1 and mass 2. Mass 1 is also connected to ground through a linear damper with damping coefficient C1, and then there's a linear damper C2 interconnecting M1 and M2. Let's say I've got an excitation F2, a force excitation, and a time varying force that gets applied to the second mass. Of course, since it's a multiple input, multiple output system, we could have also handled in this a force M1 acting on mass 1, but I'm going to leave out that. Let's say we only have a force on mass 2. So we've got a single input exciting this system, F2, force F2. And then let's say that we measure the displacement of mass 1 with a variable U1. Now, of course, since the force is a function of time, this variable U1 will also be the displacement of mass 1 will also be a function of time. And of course, it's measured from some other fixed reference. This fixed reference is such that when this whole system is at equilibrium, U1 will be 0. And then I also measure the displacement of mass 2 with a variable U2, also measured from some other reference such that when the system is in equilibrium, U2 is 0. And now I'm going to say, I analyze the case where the outputs of the system, we've got two outputs, a single input, double output system, and the outputs is U1 and the velocity of mass 1, or the speed of mass 1, U1 dot. So U2 is actually not an output of the system. Okay. Everybody happy? Now, to do the modeling, we need to set up the two equations of motions of the two masses. And for that, we use Newton's second law. And I'm not going to go through this in detail because it's really something that you've done so many times before. If you have problems with this, setting up these two equations, you need to just come and see me and I'll explain that to you. But so we have these two equations. And I've just repeated them at the top of the next slide here. So now I'm going to cast these two equations in matrix form, and this is typically the way that the vibration analysts will do this. So they create a mass matrix multiplying with the acceleration vector, where of course U1 double dot is the acceleration of mass 1 and U2 double dot is the acceleration of mass 2. By the way, it's a little bit late to say this now because I actually had to say that when we derived the equations of motion, right? But okay, that was implied. And then I've got a damping matrix multiplying with the two speeds, U1 and U2. And then I've got a stiffness matrix multiplying with the two displacements, U1 and U2. All of that on the left-hand side is equal to the excitation vector on the right-hand side, 0, because I do not have any excitation on mass 1, and F2, the excitation on mass 2. So this is typically how the vibration people would write these equations. And you can get to the state equations via this route. You can also get to it via other routes, but this is a convenient one, so that's why I've chosen to do this. I'm going to repeat this at the top of the next slide. And now I'm going to define two new variables. V1 is the first time derivative of U1, and V2 the first time derivative of U2. And this is really... Well, okay, maybe I should say this. Why do I do this? Well, I need to do this because I want to get rid of this double derivative. I know that I want to make a state space representation, and I know the state space representation is a first order representation. So I cannot really deal with second derivatives and stuff like that, and higher derivatives. So I need to get rid of them. So in order to get rid of them, I define these two new variables, V1 and V2. Because if I now substitute these variables into this differential equation, I actually get rid of the second derivatives. But note now that here I had two equations, and now all of a sudden I've got four equations. Because it's really these two equations plus these two definitions. These two definitions are the two additional equations. So let's just quickly check them out. So here I had M1 times U1 double dot, but U1 double dot will be the same as V1 dot. And so here I also have the same M1 times V1 dot. So that gives me the same term. And then if I look at the second term in the first equation here will be C1 times C2 times U1 dot, but that's the same as C1 plus C2 times V1, because V1 is the same as U1 dot, right? You get my drift here. And then the third term is C minus C2 times U2 dot, but U2 dot is the same as V2, so that is then this minus C2 times V2. And now, then that's now the 1, 2, 3. The fourth term in the first equation is K1 plus K2 times U1, and that I've retained here. That's K1 plus K2 times U1. And then next term is then minus K2 times U2 minus K2 times U2 is equal to 0, and I've got the 0 on the right hand side. Okay, everybody happy with that? And now with the second equation, I do exactly the same, and you can on your own go and confirm that this gives me the second equation that I have here. And I've gotten rid of the U2 double dot by replacing it by the V2 dot. And also on the damping terms, I've replaced it in the same way. So that's the first and the second equation. Now the third equation says that 1 times U1 dot plus minus 1 times V1 is 0. But that is exactly the same as V1 is equal to U1 dot. Okay, so this equation is the third equation in my matrix equation. And then lastly, I say that U2 dot plus minus V2 is equal to 0, which is this equation. Okay, everybody happy? So I'm going to, on my next slide, repeat just the bottom equation. And now, remember, I'd like to have a first order differential equation with just the time derivatives on the left-hand side. This upper equation is in fact a first order differential equation. It's now 4 equations rather than 2. So instead of having 2 second order equations, I now have 4 first order equations. So that's true. But on the left-hand side, I have a matrix multiplying the time derivatives, and then I've got another matrix times the state variables. So it's already becoming clear. I haven't said this yet, but it's hopefully becoming clear that this V1, V2, U1, and U2 is going to be my state variables. And so here I've got the state variables pre-multiplied by a matrix, but it sits on the left-hand side. I don't want it on the left-hand side, but that's not too much of an issue because I can simply take it across the equal sign to the right-hand side. But then still, even if I do that, I still have my state variable first time derivative being pre-multiplied by a matrix. And I need to get rid of that to get my equations in the standard form. So this upper equation is not illegal. It's simply not in the standard form for the way that we describe the state space method. So I just need to manipulate it. So the first thing that I do is I take the coefficient matrix multiplying with a state vector to the right-hand side. So that introduces a minus sign. That's okay, because I can just multiply the minus sign into the matrix. No big deal with that. And then then I'm left with, on the left-hand side, with the time derivative vector pre-multiplied by coefficient matrix, which means that I need to get rid of that by pre-multiplying the whole equation by the inverse of this coefficient matrix. And so if I do that, I end up with my with the equation actually now recognizable as in the standard form, because now I've got on the left-hand side the first time derivative of the state vector, and the order is just swapped around because this inverse matrix pre-multiplying the negative of this coefficient matrix is actually my A matrix. And this is my input vector containing zeros except for the input force F2. And so then it means that this inverse matrix here is actually then my B matrix. You can think of it like that. So I'm just going to rewrite that equation and then manipulate it to get it in this form. So what I've done is, instead of thinking of this vector with 4 elements as 4 inputs of which 3 is 0, I've said, okay, let's just say I've got a single input, in which case my B matrix, instead of being 4 by 4, becomes 4 by 1. So now this is my B matrix times a single scalar input F2, and this is my A matrix including the minus. It's the A matrix pre-multiplying my state vector, and on the left-hand side I've got my derivative vector. So with this now, I've cast the Newtonian dynamics equation of that 2 spring mass damper system into a standard state space form. Everybody happy with that? Okay, I'd like to just stop the recording here now.